So the farther down the road we can get with this topic, then we'll be in better shape. Okay. So in last Thursday's lab, it was all about ionic compounds, naming ionic compounds, writing the neutral formula for ionic compounds. This week it's going to be about Lewis structures. So just to kind of, I have a bunch of review slides. You're like, oh, you already said that. I'm like, okay. I guess it's in your notes. I don't think I repeated myself. Maybe I did. Okay, yep. So covalent bond is sharing of electrons, okay, versus transferring of electrons. We talked about covalent compounds. And remember, kind of, as we kind of did this kind of left and right thing, covalent compounds are over here on the left. Covalent compounds, molecular compounds are synonymous, you know what I mean, the same. A covalent compound can only have covalent bonds. Any ionic bond, and it's contaminated. It's an ionic compound, okay? So electronegativity, we talked about that, is basically you have two atoms that are bonded together, and that's the tendency for one of those atoms to basically hoard electrons when it comes time for that pair of electrons that are potentially being shared or transferred. In general, okay, we did this whole thing with the arrows. Electronegativity increases from left to right, and it increases up the group, which is just the opposite of size. Size increases this way and increases this way. Okay, so electronegativity. All right, these are all review slides. Linus Pauling, I know he earned the Nobel Prize in Chemistry, but those are Pauling values or electronegativity values. Remember that the greater the electronegativity value, the more it's going to want to hoard electrons to itself. Okay, then with regard to ionic bonds, there are two types of ionic bonds. And it's all about the electronegativity value of the atoms that are being bonded as to what sort of chemical bond you'll get. Large delta chis, large electronegativity differences give you an ionic bond. Smaller differences give you a covalent bond. And these, again, are the Pauling values, electronegativity values for the nonmetals. Nice little jag there. All right. This is a new slide. Okay. So, I'm going to go ahead and draw the Lewis structure, and we'll talk about what a Lewis structure is, but for water. I may have done this before. So H2O, we have what we call a central or middle oxygen atom, and it's bonded to two hydrogens. So I'll go ahead and do the little chemical bond there. Those chemical bonds actually are covalent bonds, so a pair of electrons are shared. Okay, so I'm going to go ahead and do my little pair of electrons, okay? And if we draw the Lewis structure of water, okay, one of the things we're going to see is that actually there are two other pairs or four other electrons around oxygen. But my point here is, as I circle in purple, okay, those two bonds with a pair of electrons there, those electrons are being shared. They're like joint custody. Those electrons are being double dipped into by the oxygen and by the hydrogen. So as we look about complete octets, I'll choose the color green. I can actually, and they kind of remind me of Venn diagrams with the whole overlap and that sort of thing. In green, I can go ahead and draw a circle around the electrons that the oxygen has custody over, or at least joint custody over. And if you count those electrons, you come up with 8. 2, 4, 6, 8. That's kind of how that works. We could do another little Venn diagram around each one of the hydrogens. And each one of the hydrogens has, 2 electrons. Okay, and that is like the rare gas helium. Okay, so that's kind of what we mean by they get to be double dipped. So when you draw a Lewis structure with the element boron, actually boron in its final Lewis structure only wants 6 electrons, not a complete octet, just because of how it is, if it's part of a neutral molecule. Then there are Lewis structures, and we will dabble in them a little bit. Not on Thursday, but I want you to know that they're out there, and I think I have some homework. But there are Lewis structures where you look at an element that is in period 3 or greater, and oh my gosh, that's a lot of elements. Because if you look at the periodic table, so period 3 is just like sodium, magnesium, aluminum, blah, blah, blah. So anything like that can have what we call an expanded valence, which in its Lewis structure, it's going to have, instead of 8, it might have 10, or it might have 12. Those are your other two options of electrons, okay, in its final Lewis structure. So that's annoying, but true. Okay, so let's look a little bit closer at the nature of these chemical bonds, these covalent chemical bonds. Okay, I like the title of this, a simplified or a simple quantum mechanical view of covalent bonding. So as we've been talking, covalent bonds are just where atom A and atom B share, and actually we're going to narrow it down to share a pair of electrons to form a covalent bond. Okay, so this is kind of cool, and I don't know if this works for you, but I usually say if this is atom A and this is atom B, and if you kind of consider my elbow as the nucleus of nucleus of atom A and nucleus of atom B, one of the things we talked about is that the electrons around the atoms actually have are organized in orbitals. So actually this my kind of from my elbow to my wrist could be an atomic orbital of A, and this is an atomic orbital of the other atom. Okay, so honestly, what happens, like this slide says, is in order to form a chemical bond between these two, basically they each donate an atomic orbital. There is a degree of overlap, and actually there's a strength, like I could just have just a barely overlap, or I could have strong overlap, and actually that gets to the bond strength there. Okay, so the atomic orbitals overlap, they create a bond orbital, something new, something shared, something different. In that bond orbital, that's actually going to be where your electrons reside that are part of that chemical bond between those two atoms. Is that not cool or what? It's a beautiful thing. Okay? So atomic orbitals from each of the atoms overlap to create a bond orbital, if they're going to bond. Okay? If an electron's not going to be transferred, if it's going to be shared. Okay, so what's up with these bond orbitals? Well, they have some rules. Okay, and here are the rules. Every bond orbital that's created by the overlap of two atomic orbitals must have 2 electrons in it, a bond orbital, 2 electrons. Can't have more, can't have less. And just like we've kind of talked about the other rules to orbitals, they have to have opposite spins, they have to have opposite spins. Okay, that's it. Now this is kind of a different cat. Again, this is connecting the 2 atoms. Okay. What else? Well, here's kind of a fun sort of thing. And this will kind of become apparent when you start drawing your Lewis structures, that when it comes time to connect atom A with atom B, the pair of electrons, 2 electrons that need to reside in that bond orbital, don't have to come from like 1 electron here, 1 electron there. They can both come from 1 atom. Okay? So that's kind of cool. All right. So we have this idea of a single bond, double bond, and triple bond. And I'm going to start to kind of get you thinking about this. I'm going to draw 3 structures, and they're all hydrocarbons. So the first one, I'm going to draw C2, pick a different color. C2H6. Here we go. I'm going to have 2 carbon atoms that are bonded together, and then my 3 hydrogen atoms, I'm going to have 3 hydrogen atoms around each carbon atom. Okay, so this could be, and actually Lewis structures, blah, blah, blah. This is a Lewis structure. Okay, that works. Now each one of these dashes here represents a covalent bond. Specifically, like the heading over top of it, all of these are single bonds. Well, I bet if I drew this carbon with 2 dashes, I bet you'd call that a double bond, and you would be right. The next one I want to do is C2H4, and so the way that looks is this. Okay, there we go. So, of course, we have our single bonds between our carbons and our hydrogens, but now we have a double bond between the 2 carbon atoms. If I were to ask you about a triple bond, You guys would tell me that's a triple bond probably. So actually the compound C2H2 works well for this. Now, I want you to start thinking about this. Every time you see a dash, that's a covalent bond, okay? And there are a pair of electrons for each one of those dashes. So are we good with this? That actually there are, what, 4 electrons here and 6 electrons here? Just for kicks, let's go ahead and make our little green Venn diagram. Let's see how this carbon atom came out with regard to electrons. Here we go. What do you think? So it's got joint custody here, 2, joint custody here, 4, 6, 8. You know, it's got what we call a complete set of 8 electrons around that carbon atom. Now we could pick on any. We could go up here. Let's do this carbon atom. Here we go. It's got 2, 4, 6, 8. Okay, it's kind of messy, but so each one of those dashes is a pair of electrons. Okay. Single bonds, double bonds, and triple bonds. All right. Okay. So covalent bonds are formed by the overlap of atomic orbitals from the atoms that are going to be connected together. Now there's 2 versions, and sometimes I call them vanilla and chocolate. Sometimes I call them meat and potatoes and then dessert, and actually the whole meat and potatoes and dessert goes together pretty good. There's the first to arrive, okay? There are 2 types of covalent bonds. There's the sigma bond, sometimes called the primary bond, first to arrive, okay? Primary bond, covalent bond between 2 atoms. So if you have 2 atoms that are joined together, they have to have a primary bond. They have to have a sigma bond. But you cannot have 2 atoms joined together, the same 2 atoms joined together, with 2 sigma bonds. It only gets 1 sigma bond. All single bonds are sigma bonds. So you got the whole sigma, that's a Greek letter, it's a lowercase sigma. And all sigma bonds will be oriented between the 2 nuclei. So if kind of go back to my elbows being the nuclei of these 2 atoms, okay? So then actually this sigma bond needs to be right here. I have brought some structures here. And the first structure, the C2H6, that's what this is. So we have 2 carbons, and each carbon has 3 hydrogens. So the white things are the hydrogens. And so the gray thing actually is the sigma bond. Okay, makes sense? It's connecting the nuclei of the pairs of atoms. First to arrive, sigma bond, primary bond. Well, after you eat your meat and potatoes, you can have dessert. And a type of dessert is pie. My grandma used to love pie. So anything after a single bond or the first to arrive is a pi bond. It's a secondary bond, okay? So the pi bonds are optional, but I'll tell you, if you have a double bond between 2 atoms like we had in that middle structure, the first to arrive was sigma, the second one was pi. If you have a triple bond, like the third structure we looked at, the first to arrive is sigma, then you have pi, pi. Okay, you can have extra pi, but you can't have extra meat and potatoes. So a double bond consists of 1 sigma, 1 pi. A triple bond consists of 1 sigma, 2 pi. So you'd be like, okay, so I need a pair of electrons that are going to connect these atoms, and I need to add to the sigma that's already there. Where are they going to go? Well, they are going to go outside of the region. They basically go, and I actually have a set of slides that talk about kind of the pi and the sigma bond. But the way this is basically a pair, you take a pink and a purple, and that's a pi bond. Okay, I'll show you the wrong one. This is my second structure. That's not what I'll show. Okay, the second structure. We said that's carbon, double bond carbon, Of course, hydrogen, 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 hydrogen. So in a double bond, you have a sigma bond, and then you have a pi bond. Where are the electrons going to be? They're actually going to be in a cloud, a pair of electrons, above and below your sigma bond. Is that a clue what? You might like, how do they figure that out? And I'm not sure. Okay, so that's sigma, pi, of course sigma, 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 sigma. Now let's take it up the notch. Our last one, structure we looked at, had a triple bond. That's this one. So triple bond, of course we had carbon, triple bond carbon, and of course we had singly bonded to, these are your sigma bonds. First to arrive, sigma bond. Then you need two pi bonds. Where are they going to be? Here and here. Okay. Now, the electrons, they're like kind of invisible in a way. Okay, they are, but they aren't. Okay. So actually, if we were to look at this molecule, it would look like a hot dog. This is your hot dog. Okay. So sigma, pi, pi, the triple bond. No, make me hungry. Okay? All right. So we talked about the valence electrons around atoms. The valence electrons are the outermost, they're the most important, the highest N. Not the last added. There's something kind of related to valence electrons called the valence of an atom. And I almost hesitate to relate it to valence electrons of an atom. The valence of an atom basically says, and it only works for neutral molecules, but basically it's the number of times that that atom is expected to reach out, totally in sigma and pi bonds. The expected valence of an atom. The expected valence of an atom. And we'll be working on this kind of premise or applying this in Thursday's lab. So the number of times you expect it to reach out with sigma and pi bonds. And you can get the expected valence for atoms in neutral molecules. Now, some of the Lewis structures you're going to do on Thursday aren't neutral molecules. But if it's a neutral molecule, you would expect it to reach out basically 8 minus the group number. 8 minus the group number. There's your little rule there. So I've gone ahead and done that little subtraction for you on the next slide. Again, we have two exceptions. The expected valence for a hydrogen atom, how many times is a hydrogen atom going to reach out? Once. It's pretty it's not very complicated. Hydrogen, it only had one electron, so it can only basically shake hands once. Okay, that's about as good as it can do. And I talked about boron doesn't want an octet, it wants 6 electrons, so kind of related to that, its expected valence in a neutral molecule is 3. So, what do we got? Carbon is 4A. Okay, so 8 minus its group number 4 is 4. Nitrogen and phosphorus are 5A. So 8 minus 5. See how that works? Oxygen is 6A. So 8 minus 6, oxygen and sulfur. The halogens are 7A, so 8 minus 7 is 1. Okay, so those are the number, that's using the 8 minus the group number. So on a final Lewis structure, you expect it to reach out this minimum of times. If you look back at the examples that we did with the C2H6, the C2H4, and the C2H, and you were to basically draw a circle around the carbon atoms, you actually would see that the total number of sigma and the total number of pi bonds actually in all those cases is 4. So it follows that. And like we said, hydrogen only wants to reach out once. I've seen it before when you guys do your lab on Thursday. Sometimes students just want to load hydrogen up, but it can't handle it. Okay? And boron wants to reach out 3 times. It can't handle the truth. So the expected valence of an atom you get from 8 minus its group number. And of course its group number are the number of valence electrons. Actually, visually, if you look at the number of valence electrons, it kind of makes sense. You can almost see how many slots it's got open to reach out. So we said carbon, the expected valence of carbon in a neutral molecule is 4. Also, it has 4 valence electrons. It's kind of almost a tipping point. So can you see, basically, when it comes time for atoms to saddle up, okay, to it, basically, it kind of has 4 slots in a sense. This is where I kind of picture a little kid kind of taking this toy car and going, vroom, vroom, you know, kind of parking it in those spots. Nitrogen, of course, the reason it has 5 dots around it is it has 5 valence electrons. If we're going to go ahead and kind of slot in there to those 3 slots, it reaches out 3 times. That is actually correct. 8 minus 5 is 3. Oxygen, 6A, 6 valence electrons, saddle up, reaches out twice. Now again, these are only in neutral molecules, and these are the number of sigma and pi bonds that it's expected to form. Halogen, fluorine, 7A, saddles up once. Okay, and of course neon, rare gas, inert, doesn't like to connect, doesn't like to play with anybody. So that's okay. We'll let them do that. So the kind of the Lewis structures that you've seen and that you'll be drawing, Lewis structures in general, what they do is they come up with what I call just a pot of valence electrons that all the atoms are going to contribute to. Okay, basically it's like if you were going to, in your family maybe, you basically throw everything together and then you divvy it out how you need to. That's the pot of valence electrons, okay, that need to show up on your final Lewis structure. So in that pot of valence electrons, when we'll divvy them out to everybody, and I'm going to show you the process that I think works pretty good to create your Lewis structures. I'm going to show it to you today, and we're going to hit it hard on Thursday, so I'll introduce it to you. There's a homework at the end, but I'm not going to make that due until next Monday, okay? So we're not even going to have homework due today. But how do you draw the Lewis structures? You come up with a pot of electrons, and then you go ahead and you can make those electrons do what they need to do to give everybody complete octet. Or if you're hydrogen, 2 electrons, or if you're boron, 6 electrons. So they can either be bonding pairs, okay, or they can be lone pairs. Now, do you remember the oxygen, do you remember the water molecule I kind of threw up there a little bit ago? And I had oxygen, bond, hydrogen, and then I put like dot, 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 dot. Those were lone pair electrons. So let's see how this works. I have some examples. Lone pair electrons were part of the pot that needed to be distributed. Lone pair electrons are necessary to give atoms complete octets. So whenever you see a Lewis structure like we've drawn, you know, with the carbon, double bond or triple bond or single bond, the hydrogens, think of that symbol as representing the nucleus of the atom, the nuclei of the atoms, and their non-valence electrons. And then the dashes or the lone pair electrons are kind of the pot of valence electrons that are brought to the table by all of the atoms. Okay, anytime you see a dash, solid line, think of that as a single bond, or, well, I guess, yeah, because then I do this, don't I? Anytime you see a single dash, that's a sigma bond. 2 electrons are represented there. Anytime you see a double dash right together, that's a double bond, 4 electrons. 3 dashes, that's a triple bond, 6 electrons. And just with the water molecule a little bit ago, anytime you, and they'll always be, well, mostly in pairs. Lone pair electrons mostly come in 2s. Okay. All right. So you've kind of maybe seen we have this whole north-south, kind of east-west sort of thing going on with the Lewis structures, for instance, that we looked at with the carbon, nitrogen, oxygen, and fluorine. But there is no north, south, east, or west. Sometimes when students draw your Lewis structures, you'll come in from the south, or come in from the east, or come in from the west. It's all the same thing. It's just kind of a convenient way. Those 4 sides, you've got a pair of electrons add together to make 8 electrons, which is kind of convenient sometimes. So Lewis structures are pretty flat. Lewis structures are paper and pencil, but one of the things, and we'll get to it in Wednesday's lecture and emphasize it Thursday, that if you have the paper and pencil Lewis structure, actually, and this would be important for things like DNA, RNA, you know how kind of it's got that helical shape, you can actually infer from what you see the Lewis structure as to what the shape is. So shape is an important thing in chemistry. All right, so let's look at ammonia. Let's do a few things with this one. I kind of want to reverse engineer this, if that's okay. So this is the final Lewis structure of, I get my ammonium and ammonia mixed up. Okay, ammonium is NH4+. Okay, ammonia is NH3, the neutral molecule. So by reverse engineer, this is what I mean. Let's come up with the pot of valence electrons. Okay, there's one nitrogen atom. This is how I do my pot of valence electrons. Pot of electrons. Not just any electrons, valence electrons. The element nitrogen, there's one nitrogen atom. We know how many valence electrons it brings by looking at the periodic table. So it's 5A, so it brings 5 electrons. Cool. There are 3 hydrogen atoms, the element hydrogen. And hydrogen only has 1 electron, and it is a valence electron. So there we go. So for hydrogen, I got a total of 3 electrons. So my pot from the formula is 8 electrons. So in a way, like I said, I'm kind of reverse engineering this. So those 8 electrons need to be distributed on the Lewis structure. So let's see if we do have 8 electrons here. So it's looking pretty good. I see 2 electrons for each one of these sigma bonds, covalent sigma bonds. And then I see 2 electrons here. So that's my pot of 8 electrons. That's one check. Okay. And then the other thing is with regard to complete octet. So if we look around the nitrogen atom, we could circle the electrons it has possession and or at least joint custody of. And it does have a complete octet. We could circle the hydrogens, and they don't have an octet. They don't want an octet. Okay, so that works good. One last check here is let's look at the expected valence of a nitrogen atom in a neutral molecule like this. We said the expected valence is the number of sigma and pi bonds that an atom's going to reach out. So nitrogen is 5A, so 8 minus 5 is equal to 3. So that is what I call the expected valence. Okay. I'm liking it. You see it reaching out 3 times? 3 sigma bonds. Okay, so it's cool. So again, I would give that person an A. Let's do a similar thing for this. The formula H2CO. So again, if we kind of reverse engineer, I usually just kind of take it the way the formula is. So with regard to hydrogen, there are 2 hydrogens, each one of them bring 1 electron. Okay. With regard to carbon, there's 1 carbon atom. It brings 4 electrons because it's a 4A. That's how many valence electrons it has. Oxygen, there's 1 oxygen atom. Oxygen is a 6A. So I'm getting 12. So remember how you count these is I've got 2, 4, 6, 8, 10, 12. That looks good to me. Okay, let's look for a complete octet. Around the carbon atom, got 8 electrons. Around the oxygen atom, 2, 4, 6, 8. I got 8 electrons. It's looking good. The last check, let's look at expected valence. So for carbon, the valence is 4. So remember, valence is sigma and pi bonds. So let's see, 1, 2, 3, 4. That looks good. Okay, for the element oxygen. Oxygen is 6A, so we take 8 minus its group number 6, so its expected valence is 2. 1, 2. See how that works? Reverse engineering, that's what they do to UFOs. I heard that one time. Probably a science fiction movie. Okay. The last thing is hypochlorite. And remember that the halogens, they form 4 oxyanions, ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Arr. Okay, this just happens to be hypochlorite. This is the one you want to need to know. Okay, so let's see, chlorine. Okay, it's a 7A, so it's got 7 electrons. Oxygen, it's again a 6A. Now, here's the deal. If you're drawing the Lewis structure of something that has a charge, you have to accommodate the charge. The fact that this is -1, guess what? We add 1 electron. So I usually just say charge. Because of the charge, I'm going to put +1 electron. All right, so I got 14. Let's see, 2, 4, 6, 8, 10, 12, 14. Bingo. Now, how are we doing with complete octet? Pretty good. Set of 8 electrons. Yep. And then the last check that we've been doing, the expected valence. Since this is not a neutral molecule, the expected valence goes out the door. Let's check it. So oxygen, for the last one we did, we said oxygen's expected valence is 2. Okay, it's only reaching out once, but it's a polyatomic ion. Also, the expected valence rules don't always work, but they just generally do. Sometimes students can just like visualize it and kind of come up with a structure. I don't know, I'm not that good at that. Okay, so complete octet, rare gas configuration are kind of synonymous. Okay, and I kind of already mentioned this, that most atoms will want a complete octet. The problem is, though, and we won't in lab, but I think we dabble with it in some of your homework, have atoms that actually have a expanded valence. And that means it's not an octet, it's actually, instead of 8, it's 10 or 12 electrons. All right. So this one reminded me of, like, I guess we don't do one. Okay. I feel like I've already said that. Okay, so I guess I don't go through a full-fledged example for you yet, but that's okay. When we do it, basically we come up with a number of valence electrons. Oh, I think I do. I must have it in my slides, or not. You don't have it. Come up with the pot of valence electrons like we've been doing. You determine how to arrange the atoms. And my hint there is, and you'll see it in the write-up for Thursday's lab, you put lowest electronegative atom in center. You might be like, well, what if there's not an obvious center? Well, there will be for the ones you have in your test or for the lab. Okay, put the lowest electronegative atom in the center. How are they arranged? And then once you know how they're going to be arranged, go ahead and do a preliminary Lewis structure. Draw in those first bonds, the first to arrive, the sigma bonds. And then whatever you have left over, you go ahead and sprinkle it around. And my hint for in the lab is to, let's see, I think I worded it this way, satisfy terminal atoms first. You know, if you have leftover electrons that didn't make it part of your sigma bonds, satisfy terminal atoms first. Okay, so let's just say you distributed all of your electrons, your pot of valence electrons have been distributed, and it's usually your atom that's in the middle that just doesn't quite have a complete octet yet. Basically, I'll call it the conversion process. You basically convert lone pair electrons to, you swing them in. I'll use this one. You swing in lone pair electrons to form a pi bond. So you guys don't have this now, do you? What if you go to the next part? Keep going. Keep going. There. Okay. So if you would go to part 9. Part 9, are we all on? Good. Okay. So let's go ahead and knock this one out. So the pot of valence electrons is kind of like you've been seeing me do. You focus on each element. Hydrogen, there's one hydrogen atom. It has one valence electron, so there's one electron right there. Carbon, there's one carbon atom. It's a 4A element. It brings 4 valence electrons. Oxygen, there are 2 oxygen atoms. They are 6A, so 2 times 6, they collectively bring 12 electrons. Now don't forget, since this has a -1 charge, we have to kick in 1 for the charge. If we add all that together, we get 18. Right? Okay, so that's step number 1. They're all kind of fun, actually. Step number 2 is to come up with how they're arranged. Now, like I said, the ones you're doing in lab and on your test, you'll have something in the middle. You could go, like, will hydrogen want to be in the middle? No, hydrogen never wants to be in the middle, only wants to reach out once. Then your other options are putting carbon in the middle with 2 oxygens and the hydrogen out, which kind of makes symmetrical sense to me. Or putting one of the oxygens in the middle and having stuff branch out of that. Well, let's find carbon and oxygen on the periodic table. And as it turns out, it's kind of convenient, they're in the same period. So we want the lower electronegative atom in the middle. So we said electronegativity increases from left to right, so carbon is the lower one. So we're going to put carbon in the middle and branch those other 3 atoms off. So that's kind of our what we call our preliminary Lewis structure. So this is our prelim Lewis structure. And so right now, can you see with just those sigma bonds, I have used up 6 of my 18. So I have a pot of 18 electrons. I got to use one way or the other. So here I have 6 electrons. Okay, so I have 18 minus 6, so I have 12 electrons remaining. Okay, and do you remember where I said you satisfy the outside or terminal electrons first? What you're going to see on the next slide is actually I'm going to focus on giving my oxygens a complete set of 8 electrons before I turn my attention to my middle atom. That's just the way it works. It works out better that way. So as it is, oh my gosh, each of those oxygens only have 2 electrons. If they want a set of 8, I'm going to have to take 6. I'm going to have to split my 6 up. I'll go 6 and 6, right? Okay. So our next, now this is still preliminary. I'll show you why this is preliminary. This will be like our step 4, 3 and 4, I don't know, when you guys are doing them in lab. So now I have my 18 electrons distributed. My oxygens are great. My carbons, my middle carbon atom, not quite so much yet. Okay. So remember, my hint was to swing. Okay, so literally you are going to swing a pair of lone pair electrons from either your north oxygen or your east oxygen. You're going to swing them in, just one. And so the oxygen keeps custody of it, but it also swings in and shares with the carbon. What you have made then is a double bond. You have added basically a pi bond then. Okay. Now actually part 9 is going to go a little bit further into something called resonance structures. We've got time. So you're like, which one do I swing from? The answer is either. And honestly, sometimes you can end, well, I say either, sometimes it's more obvious than others. This time it's not obvious. You could isotopically label them, like you could get different isotopes of oxygen, and you could know which is which. And you know where the swinging comes from, and it's either, okay? So notice in this case that I swang from the north one, you know, you're like, really? I could have done the whole east one too, and it would have been the same diff. Now, another thing though about this particular Lewis structure, so actually this would be a final Lewis structure. We can do the checks, we can make sure everybody has a complete octet, and they do. Okay, so of course we have 8 around this oxygen, we have 8 around the carbon, we have 8 around this oxygen. Everybody's got a complete octet just by swinging that lone pair electron in. But I also wanted to point out, anytime you have to draw a Lewis structure of something that's charged, you always have to put it in brackets and put the charge outside. On your test, each Lewis structure for your Unit 4 exam is going to be worth 3 points. You lose 1 point if it's a polyatomic ion. You don't put it in practice with the charge outside. Okay. So we've actually gotten into, oh, well, don't do that assignment. I'll talk more about swinging from the whole north and east some other time. Is that really the next slide? Mm-hmm. Where are we at?
That's where we were at.
Oh, okay. But it doesn't do that. No. No. Okay. This should be. Is this the last slide in 7? Okay, good. So if you want to go back to 7 and make a note that actually these will be due, and I'll try to remind you in lab, but these will be due next Monday. And we'll make them for, I'll double check, but I'm leaning towards, yeah, these would do, I was thinking about for lab credit, but these will be due Monday. That's the Monday before Thanksgiving. Oh my gosh. So, okay? All right. Very good. That's all I got today. So nothing due Wednesday. And Wednesday we'll do part 8.